All right, let's roll. So how's that homework going? How are those identities? How do y'all feel? You feeling any more comfortable? I was in my calculus class yesterday, and in my calculus class we're covering one of the harder sections, probably the hardest section, and it's the second day that I've gone over this material, and so at the end of yesterday, I guess I had shown them probably a total of maybe 12 examples over 2 classes. I was like, so how do y'all feel? Let's take a vote, and I gave them a choice of feel pretty good, and oh shit, you know? And nobody was feeling good, and nobody was in the middle. Everybody didn't feel good about it. So, how do you feel about identities? Do you all feel like, how many of you are like feeling pretty good? Yeah? The one that I did? The one that I got stuck on for a while? Yeah, that was a monster. How many of you feel, like, okay, middle of the road, all right? And how many of you still just, it's okay if you still feel like you're struggling with it? Okay. You just got to keep grinding away at this, I don't know what else to do other than keep practicing. Come by and see me if you need help. Are the solution videos, are y'all able to use those? Are they helpful? Okay, good. Good. Yes?
Do you know what this pencil pen is?
Do I what?
That pink pencil?
The pink pencil?
Do you know what that is?
This one right here?
Yeah.
Does it look like
I
yours?
think I
It
might
probably
have
is.
I lost it. Okay. Thank you.
Was it 0.7 millimeter?
Yeah.
Okay. All right. Well, if you got my email, on our calendar we're supposed to have a test today. And we didn't really talk about that too much. So I didn't think we would do that. And then a student emailed, who emailed me? Okay. So we're going to have our test on Thursday. I don't think anybody wants to do it after spring break, right? I think that's a terrible idea to try and come back and take the test. So our test will be on Thursday, and I will talk about it at the end. Just make sure you give me 10 to 15 minutes. Don't let me go over. All right, so maybe around 1:25. No, wait. 12:20 or so. Okay? Stop me. We are going to cover something new today. Unless there are any questions that you want me to go over, as long as they weren't homework problems, which I should have a video for. Anything? Today's material, I'm actually going to let that kind of be up to you as a class. Because you may see it and like it, and so you may want to have it on the test. All right? I don't know about like it, but you may prefer it over some of the other stuff. So why don't we talk about that at the end? Like, would y'all like to see a couple of these? 8.3, trigonometric equations. I'm going to put 3 stars next to this section. When I'm sitting there on my first day of calculus, I usually tell my students, that have just come from pre-cal, I say, the things that are most important in terms of what you need for calculus what you need for calculus coming from pre-cal, what the topics are, you need to have a very, very good, solid knowledge of the unit circle and all the different angles and the common values and things like that. You've got to have that. And then the next thing I tell them is you must be able to solve trigonometric equations. Those are like top 2. All right, so this section is very, very important, all right, for later on, for what you're going to be doing. So let's start out. I'm going to start out with, well, what the title means. Equations, right? That involve trigonometric expressions. So just remember that we have all sorts of equations that we've dealt with in our lives already. That right there is an example of an equation. It falls into a category called linear equations, right? That's linear. Does everyone recognize that as linear? And there's a set of steps to solve this, right? What would be the set of steps to solve this linear equation? -5, right? So you're isolating x, right? You're isolating x. That would be the method. Okay, so what if we change it to, well, let me do it this way. What type of equation is this? It's not linear. This one's linear, right? This is a quadratic equation. Yeah, well, it's still a quadratic equation. It's an equation that has a power of 2 for x, so it is a quadratic equation. To solve it is not the same as what we do for this, right? For this, you isolate the x. You move everything around, get the x by itself. For this one, you do not isolate x. You move everything to one side first, let it equal 0, and then you either factor or use quadratic formula, right? So there's a set of steps that we use to do something like this, right? What other types of equations did we see? How about like this? That's an equation, right? This was called a rational equation. And the way we solve rational equations is we find the greatest common divisor or greatest common factor in the bottom, and we multiply both sides by it and clear the fractions out. And then once you do that, you'll be left with either like a quadratic or a linear. But there's a process for this, right? What I'm trying to get you to see is that there's a whole slew of different types of equations you've already done. And each one of them has their own sort of like way of doing them. Here's another one. Root x plus 1 minus 4 equals 1. What type of equation is that? Remember the name or no? It's okay if you don't. It's called radical equation. Anybody remember the process for solving this? You will square both sides. You first isolate the radical, so you'd bring the 4 over, and then you square both sides of the equation. And then for this, you had to be careful because you could get extraneous solutions. You had to go back and check your answers and stuff. You should check your answers on all of these, but yeah. So now what we're going to do is we're going to introduce a new type of equation. And these are going to be called trigonometric equations. All right, that's what this is about, a new category of equations. But as long as we have a trigonometric function in there and we have equal sign in there, it's a trig equation. So let me start with a very, very basic one. Sine x equals 0. Would everyone agree that that is an equation and that it involves a trigonometric function? Okay. So what is the process of solving this? We haven't talked about. That's what today's about. Think about what this is asking you. It's saying, give me the value of x that would give you 0 out here, right? Value or values, plural. There could be more than one x value that gives you 0. So does anyone have an answer for this?
Are we going by the radians or whatever, right?
Whatever. Can you give me an angle that would spit out 0?
It'd be like 2 pi, like 0.
2 pi?
Yeah.
Okay.
You could just say n pi, right?
N pi?
Yeah.
Could you? Maybe not.
No.
Can you focus here on a fraction in a way?
I'm going to go back to the unit circle. I told you this thing is going to be so important to us. Today it's important, very important. When we say sine of x equals 0, we're saying at what angle is the y coordinate 0, right? And that's going to happen here or here, right? Those are the only two places on the unit circle where our y coordinate is 0. Now, if I ask you to give me all of the possible angles that are represented by these 2 points, there are an infinite number of them, right? 0, pi, 2 pi, 3 pi, 4 pi, or you could go 0, negative pi, negative 2 pi, negative 3 pi. So all the multiples of pi, right? Do you remember me talking about this a long time ago? How do we write this answer? This is why for today. So I could say the solution to this is x equals n pi. Remember what n is, right? N is an integer. If you don't remember that from before,
So it can't be a fraction.
it cannot be a fraction. N is an element of the double struct z, which really means that it comes from the list of all integers. It cannot be a fraction. Although, technically speaking, these are fractions, 2 over 1, 3 over 1, but I know what you mean. All right? That should take care of all the answers. Is that clear? Sure? All right, that's it. That's the answer. N pi. X is n pi. Now, let me ask you a different question. I'd like for us to do next example here. These are obviously going to get harder. All right. Solve sine x equals 0 on negative pi 6 pi. Now look at the way I wrote that. Negative pi with a bracket, 6 pi with a parenthesis. That means you're only allowed to give me the answers, you only need to give me the answers between negative pi and 6 pi. So if I were going to be doing this problem, the way that I would do it is I would still go about it the same way. I would do this, and I would say x is equal to n pi, all right? But I'm no longer going to be giving this as my answer. I want to actually list out all of the answers in here. So what I can start doing is almost making like a table and giving different values of n and seeing what comes out. N pi is what's going to come out of this. So if n is 0, what do we get? 0 times pi? We get 0. Okay, that's one answer. What if n is 1? What do we get? Pi. And then if n is 2, 2 pi. And we keep doing this until we get out to what? I know maybe this seems too obvious. I'm going to stop at where? Am I going to include 6 pi?
Oh, yes, yes you are.
Am I? The parentheses here,
Oh, I'm sorry, I messed
right?
up.
It's all right. But the parentheses means do not include 6 pi. So even though 6 pi is part of my general solution here, it's not part of the solutions here. So 0 pi, 2 pi, 3 pi, 4 pi, 5 pi, no 6 pi, right? What about, we never let the n's be negative, did we? So let's start letting the n's be negative. So if n is negative 1, we get negative pi. Does negative pi live there? Yes? Okay, so we'll keep that one. And then what about negative 2? Negative 2 pi live there? No, so not there. So your answer to this, we're done. As soon as you get to negative 2, you don't have to keep going. So the solution to this right here is, you have to list them out. I'll go in order. Negative pi, 0, pi, 2 pi, 3 pi, 4 pi, 5 pi. Understand? Let's keep with the theme of easy first, okay? Sine x is 1. So I want us to solve this. And notice I did not give us a restriction, all right? I have not given us this. So that means I want all the answers, all infinitely many of them. Start with the unit circle. Where are we at? Where am I going to put the dot on that unit circle? At pi over 2, which is straight up, right? This is the only place where your y coordinate is 1. Now let's see if you remember. I tried to introduce you to this very early in the semester when we first started talking about angles. How can I represent all infinitely many answers here? I have to start where? At pi over 2, and then to get back to it, what? I add an entire revolution of 2 pi, right? And then to get back again, 2 pi. So how do I write it? Pi over 2 plus n times 2 pi, or you can put 2 pi in. It doesn't matter where you put the n here, okay? You can have it in front or in the back, but it has to be separate from that. So that first part is telling you where to start from, right? And then the second part tells you how much you need to go around by to get back to it. We good? Sure?
And the end, you just have to remember to throw it on there?
You have, oh yeah, you can't miss the n. Because if you miss the n, that means you only have one answer. And there's an infinite number of answers there. So this gives you the full revolution, and this is basically where you're going to be starting from. So you're starting at pi over 2 and then starting to do full revolutions. And remember, n can be negative, so that means you could go counterclockwise or clockwise, but it's a full 2 pi revolution. Okay? Let's try something a little more challenging. Yes?
Do we have to write down every possible solution for that?
No. If it says solve and it does not give you an interval, then this is your answer. And this is referred to as the general solution. It is the general one. It includes all of the answers. Okay?
Okay, because the other one said on negative pi.
To 6 pi. That's right. For that one, you actually have to start making a table and... Okay, what about this one? What's the difference between this one and the last one? Well, it's squared, right? So let me ask you this. If I gave you this equation and I asked you to solve for x, most of you would be okay with the idea of taking the square root on both sides? And then this would turn into a plus or minus, because when you take the square root, you have to do plus or minus. Agreed? So if I take the square root on both sides here, then I'm going to get sine x is plus or minus 1, right? So this means you're actually looking at two different points. You're saying, where is the y coordinate 1 or negative 1? And so this picture is going to be a little different. It's going to be like this now. That's where it's 1, right? And this is where it's negative 1. Yes? That's the picture? Okay. What was your name, sir? Back. Brandon, I'm going to ask you, I'm going to put you on the spot. Because this will mean whether or not you get it. So, Brandon, you need to go from here and start jumping around here and then back and then here and then back. So give me the starting angle that you're going to start at. Pi over 2, okay. And then you're going to add something to that, right? How much do you need to add to jump straight across to the other one? Pi, right? So I'm going to put pi and then n, because that's multiples of pi. So I can go 1 pi. If I go another pi, I'm going to be back up here. A third pi will be back down here, fourth one. Do you see how that works? Okay, so that's it. That's your general answer.
So we wouldn't, because of that thought down there, we cannot put 2 pi.
2 pi, well, what that would do is it would take you back here, back here, back here. You'd never get there, right? So this will just, it jumps you by pi each time. And since they're directly across from one another, you just keep jumping back and forth between the two. Make sense? Okay, yes.
And we can go the opposite way as long as we change the n to negative at some point, right?
Opposite
Are we not
way?
allowed to go back clockwise on this?
Well, n can be negative.
Yeah, that's what I was wondering.
So it's already built in.
Okay, cool.
It's built in because this says you're going to add multiples of pi, but they're either going to be positive or negative.
That was,
Yes.
That's what I was talking.
Yep. Just remember that n comes from the list of integers, both positive and negative. Let me ask you something. Would a student be incorrect to have given me this as their answer? Would that have been incorrect? Nope. This is fine. Because where they're going to go is they're going to start at negative pi over 2. Okay? And then they're just going to start jumping by pi again. And once they jump by pi, they're going to be doing the same jumping. They're just starting in a different place. But they will generate the same list of answers that the person that did the top one did. Yes?
And you could put minus pi in then, right?
You could put minus pi in here because that would take, it would be taken care of. If these were negative, then they would become positive, and if it was positive, it
It's
would
more
be.
complicated, but you could.
Yeah, you could. Yep. I mean, you could do pretty much anything that you wanted to think of. Like that would work too. That means you're starting at 5 pi over 2. So that's like 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. So you're starting there. But then you're jumping around by pi. Yeah, let's not overcomplicate it, but yes. All right, so there's not like a perfect, unique answer that everybody has to get. But if we're all kind of following the same logic, our answers should look similar. All right, let's try something else. This was like a linear equation. That was more like a quadratic. Let's switch it up. Let's go to cosine. I feel like we're leaving cosine out. Okay. What does that look most like from college algebra? Does that look like a linear equation, quadratic, rational, radical? Looks a lot like a linear equation. Almost looks like 2x plus 1 equals 0, doesn't it? And so here we would isolate the x, wouldn't we? Over there, let's try and isolate the cosine x. Let's try and isolate this. Okay, so we would first move the 1 over, subtract 1 on both sides, and then we would divide by 2. Agreed? So you get something like this. Cosine x is negative a half. Are we all good with that? This one is different. This one's going to be different than the last examples I've done. Since we're looking at cosine on the unit circle, which coordinate is that? The x coordinate. And we're trying to figure out where the x coordinate is what? Negative 1/2. Where's the x coordinate negative 1/2? And that, you'd have to refer back to your unit circle, happens here and down here. Those angles are not straight across from one another, are they? Now, do you know what this angle is right here? In radians. 2 pi over 3. 120 is not wrong, okay? But we're just trying to get used to the radians. So 2 pi over 3. What about this one? This is 4 pi over 3. So think about this. If I start at 2 pi over 3, am I going to be able to jump to here and then rotate by the same amount and get back to this? They're not directly across from one another. So to jump from here to here, it's not the same jump getting back. Does that make sense? Yeah. So you have to actually deal with these separately. You're just like ignore this one, give me the general solution for that one, and then ignore that one and give me the general solution for that one. We're going to have 2 groups of general solutions. right? So first one, x is equal to our starting angle, which is 2 pi over 3. And then how much do I need to jump by to get back to it? Full rotation, so 2 pi n. Right? That takes care of this one. Right? Now, for the next one, so I'm going to put here, or x is equal to what? So 4 pi over 3 is where we're starting. And then you got to get back to that same point. So full rotation again, 2 pi n. Yes?
So do we put both of those? Or
Yes.
just one?
Nope. Have to have both. Because if you only put one, you're only going to get this answer. You're going to miss an infinite number of answers. Yes?
You put or and? It's or, because it can't be both.
It's, no, it's saying that your solutions are from this list or from this list. Think about it this way. This might help. Let's say we have this quadratic. No. Let's say we have that quadratic from college algebra. So this quadratic equation, you solve it, and you get two answers. X is 3 and x is -2, right? We do not say that the solution is x is 3 and -2, because that would mean that x has to be 3 and -2 at the same time. Pardon?
Can you put commas then? Whenever you
Instead of
write
writing
the
or
equation.
to save space, you can just write it on the same line.
You don't even need to write or. I don't care if you write or at all. Just box the two separate ones. Yeah.
What if we put 2 pi over 3, comma, 4 pi over 3 plus 2 pi n?
No.
No.
No. Just write two different ones.
Just box it.
Don't complicate it.
Yeah. All right. I have another question for you here. So far, are these seem better than the identities? Or okay. So I want us to solve this again. Look, all of these problems are going to be solved. Okay, I don't want to write solve over and over and over. 2 cosine x plus 1 equals 0 on -2 pi, 2 pi. All right, so now I have thrown in an interval, which means the general solution will no longer be acceptable. I need all the answers that are there, all right? So we would go through the work, and we would get our two same general solutions, wouldn't we? We would get our two general solutions just like this, right? Now, that's not enough. We need to start plugging in some values of n and spitting out answers. So before you do it, before you start plugging in values of n, I want you to please look at something. I don't want you to get too far ahead of me here. Look at this. So don't write this down, all right? But just look at it. If I plug in n, and then I'm going to be plugging it into this, right? 2 pi over 3 plus 2 pi n, right? All right, if I plug in 0, I think 0 is easy, right? Because 0 just kills this off. This is just gone, and so you're left with 2 pi over 3. So that first one's not too bad. Okay, if n is 1, we're going to have 2 pi over 3 plus 2 pi times 1, right? Which is just 2 pi. And then what are you going to need to do if you're going to give me a nice clean answer there? You're going to have to put them together, aren't you? You have to get a common denominator. Which means you're going to have to rewrite this as over 1. Then you have to multiply the top and bottom of this by 3, which gives you 6 pi over 3, right? And then you combine this together, you get 8 pi over 3. Agreed? And if I did the next one too, I'd have to do the same thing, combine. Next one, I would have to combine and keep on doing that, right? It can become a pain in the butt to do that. So instead, what I recommend you do is get your common denominator here. And you only have to do it one time. So let me show you how that's going to work. I'm going to rewrite this as over 1, and this is over 1 here. And then I'm going to multiply top and bottom there by 3. So we're going to get 2 pi over 3 plus 6 pi n over 3. Y'all follow what I just did? Now put them together. Is that 8 pi on top? Careful. No, it's not. It's 2 pi plus 6 pi n. Because see, I don't know what n is yet, right? Over 3. That version of it is a lot easier to plug numbers into. And if I do the same thing over here, I will get 4 pi plus 6 pi n over 3. Y'all follow me on that? I'm just getting common denominators between in the general solutions. Now let's make a table. But now instead of using that, I'm going to use this. 2 pi plus 6 pi n over 3. And let's go ahead and start cranking these things out. So what happens when I plug in 0? What happens when I plug in 0 right here? That goes away. We just get 2 pi over 3. What happens when I plug in 1? That becomes 1. This is 6 pi. 6 pi plus 2 pi. 8 pi over 3. I'm going to do one more, even though I don't need to. I'm trying to illustrate, and I'm hoping that you're seeing why this is like faster. If I plug 2 in here, I'm going to get 2 times 6 times pi, that's 12 pi, plus 2 pi, that's 14 pi over 3. You see how that just starts to work faster because you don't have to get commons each time? Okay, so you get, I forgot what I said, 14 pi over 3? Okay, now I should not have done the last one because at this one right here, I should have stopped. Why should I have stopped right here? Or should I have stopped? Yeah, let's see. Where am I allowed to go out to? 2 pi? Right? That's the biggest I can be. Is 2 pi over 3 within that interval? Yes. Here's the way you can tell. 2 over 3, 2/3, is smaller than 1, isn't it? So this is less than a pi. And we're only allowed to go out to 2 pi, right? So that's in there. What about this one? 8/3. 8 over 3 is bigger than 2. So that means I would be outside of this. So I'm not going to have, does that make sense? I'm using that 8 over 3 to determine that number is bigger than 2, and I'm only allowed to go out to 2 pi, so I throw that one out. And do you see, so I didn't need the 14 over 3. Okay, now that was me making my list using this one, right? I still haven't looked at some negatives. How about -1 in this list? What if I plug in -1 here? Doesn't that become -6 pi? So 2 pi, take away 6 pi is -4 pi over 3. Is that in there? -4/3 is a little bit bigger than -1, right? So like on a number line, here's 0, here's 1, here's 2. So -4/3, -4/3 is bigger than 1, somewhere around there, right? I'm allowed to go all the way out to -2 pi. Yes or no? I'm just looking at, it's almost like I'm looking at the coefficient of the pi to make sure that it's not outside of the coefficients there. So that one's good? What about -2? So what happens if I plug in -2 here? -12, and then, so that's going to be -10/3. This number is like bigger than 3, so you're outside. So that's no good. Am I done? No, I've only done this one. I've got all the answers in that one now. I need to go look at the other one now. This is a little tedious, isn't it? With the table. That's why I like the general answers, because the general answers, it includes all these answers, and it's pretty straightforward to get to it. So far, how many answers do we have? So far. Let's see, this one was no good, right? I forgot to, this one was no good, right? So we only have 2 answers so far. All right, to do the next one, to work with that one, I'm going to create a table again, and I'm going to put 4 pi plus 6 pi n over 3. I'm going to let n be 0, 1, 2, negative 1, negative 2. I'm just going to see how this works. If I plug in 0, I get 4 pi over 3. That works. What if I plug in 1? 10 pi over 3. Too big, right? It's too big. 10 over 3 is bigger than 3, so that's not going to work. Okay, so I don't need to do 2. How about negative 1? What do you get? Negative 2 pi over 3. That works. How about negative 2? You get what? Negative 8 pi over 3. Does that work? No. Because again, negative 8/3 is going to be past negative 2. So I have 2 answers here. So the solutions to this equation on this interval are, and I'm just going to put them in any order here. I had 2 pi over 3. I had negative 4 pi over 3. And I had 4 pi over 3. And I had negative 2 pi over 3.
You don't require us to do the x such that all of that?
No, it's okay. I mean, you can if you want, but we're saying that x has to be these, right? Any of these? Anything out of that list of numbers? I'm sorry? You don't have to put them in order. All right? I'd like for us to go back and revisit the first problem that we did. What was it? Sine x is 0? Right?
The very first one?
Very first one was sine x is 0?
Yep.
Okay. Check this out. I want to solve this. I'm not giving us an interval, all right? So we're not going to have to make a table, which is good. We're just going to get a general solution. It's going to have an n in it somewhere. The difference between these two, obviously, in the first one is that 5 in there, right? You may not just pull the 5 out. That 5 is trapped inside of the sine function. So if you want, you can put the parentheses around there, but that 5 is stuck in there. Same question, though. Go to the unit circle. And this is saying, where is your y coordinate? 0, right? Which happens here and here. And normally what we would have done, like in the first problem we did, is we said x is equal to n pi, right? X is n pi. But that's because the argument was x. We said x, the argument, is n pi. This time, our argument is 5x. So what we need to do differently is we need to write 5x is equal to n pi. That doesn't seem like a big difference, but it makes a big difference. Because I need to divide now by 5. And I get, oops, I switched the order, doesn't matter. I get that. Now let me try and prove to you that this is it. Just give me some values of n here. So if n is 0, what does this turn out to be? Well, 0, right? Plug 0 into here, right? And you're going to get sine of 0, 0. Check. Now, what if n is 1? Our answer should be what? Pi over 5? Right? If I plug pi over 5 right in here, what do I get? 5 times pi over 5. The 5's cancel, and I just get pi. And sine of pi is 0, because that puts you here. Now let n be 2. If n is 2, we get 2 pi over 5. If I plug 2 pi over 5 right here, the 5's cancel. I get a 2 pi. Sine of 2 pi, that's this one, that's 0. So you see, you have to have that 5 in there to compensate for this 5 right here. Let's try another one like this. How about this? I think I'm ready to kind of throw you into the fire here. 4 sine squared of 3x minus 1 equals 0. This is a good one. We did a sine squared earlier, didn't we? And we wound up like taking the square root on both sides. Can we do that here? What do we need to do first? Move the 1 over, divide by 4. Okay, let's do that. So I'm going to move the 1 over algebraically, becomes sine squared of 3x equals a quarter, right? 1/4. And now I'm going to take the square root on both sides. And when I do that, the left side will be sine 3x. The right side will be plus or minus the square root of a 4th. What is the square root of a 4th? It's a half. You're taking the square root of the top and bottom separately. So this is saying sine of 3x must be plus or minus a half. What should I do now?
We did just a second ago with the argument.
Okay, I'm going to do something with that 3x, but
So we gotta go to the points where.
okay, good. So we need to go to the circle right now. Yep.
Circle where the points equal positive 1/2 and negative 1/2.
What points? What do you mean points?
What is it, 2?
Which coordinate are you looking at? The y's. Okay, so now you're saying where are the y coordinates positive 1/2 and negative 1/2? That's here, 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 and here. Agreed? What's this angle? Pi over 6. That angle? 5 pi over 6. 7 pi over 6. 11 pi over 6, right? But I want the general solution that includes all of these. So let's see if y'all are really catching on to this. I need right now my argument, 3x, to be equal to, not just x, right? 3x needs to be equal to something. Let's see. So 3x has to be equal to, okay, pi over 6 would put me here. Is there any way you can jump around this thing and knock out any of these other solutions?
Around by half. By pi.
if I go and rotate by pi, I'm going to be here, right? And then I go pi and I'm going to come back. But there's not a clean way to jump from here to here, because the next jump would have to be smaller, then bigger, then smaller. So what I'm going to do is I'm going to knock these out in pairs. I'm going to do these two at one time, and then I'm going to do these two with a different set of solutions. So this first group right here, you said that 3x, the argument, has to start out at pi over 6, and then jump by how much? Pi n, or n pi? That's one group of solutions. The second group of solutions is that 3x has to be equal to, now, how do you want to get these? Start at 5 pi over 6, and jump me across to the other one, so pi n again, or n pi. We're almost there. Are there any questions on that part? Divide that by 3. So x is equal to pi over 18 plus pi n over 3, or x is equal to 5 pi over 18 plus pi n over 3. I don't like the way I wrote that. There are your two sets of general solutions. What do you think? It's all right? All right, just let's be skeptics here. I'm just going to pick a value of n, -4. I just kind of like randomly pick that, all right? Now, you pick for me, because n's got to work in both of these. So which one do you want me to do? Left one or right one? Left one? OK, so I'm going to plug -4 into here just to see what I get. All right, I'm going to plug -4 in right there. If I do that, I get pi over 18 plus 4 pi over 3. Do you all agree with that? Now, I'm going to get a common denominator. So 6 here, 6 here. I'm going to get pi over 18 plus 24 pi over 18. And when I put those two together, I get 25 pi over 18, right? OK, so if n was -4, it spits this number out. If I take that and I plug it into that original equation, I better get 0, right? So let me check and see if we did it right. Right now I'm just showing you that this does create all the solutions, all right? So I'm just going to try it. Here we go. You could plug any number I'm just showing, like, should we believe that these are right? Well, let's just pick one and see if it's wrong, then this is wrong, right? OK, so I'm going to take 4 sine squared of 3 times 25 pi over 18 minus 1, and I'm going to hope that that's 0, right? That's what I'm doing. That becomes a 6 down there, doesn't it? Still there? OK, let's see where this is. If I start counting by pi over 6s, I have like pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 pi over 6, 6 pi over 6, 7, 11, 12 pi over 6, right? All the way back around, 24 pi over 6, 25 pi over 6, that's where I'd be, right? What is the y coordinate there? Sine of that. What's sine of that? Half. So this is really turning into 4, and then we always do this sine part first before we square it. So 4 times, you said it was a half? A half, but then I'm going to square it, and then minus 1. And then what's a half squared? 1/4. And what's 4 times a fourth? 1 minus 1? 0. So it checks. I'm just showing you, like, this list of answers is all infinitely many solutions that solve that equation. Yes. Just randomly. You could have given me another end, and I could have plugged into either one of these, and I guarantee it would have worked. Like it would have spit out 0.
What I was saying is,
Oh, did I put 4 in instead of -4?
Yeah.
Oh, I did.
That equals 0.
No one, wait a minute, hold on. Why didn't you, no, you should have told me. This, because I put 4 pi, right? Okay, just change that to a plus.
Okay.
I
Yeah.
don't think it matters, that's why it's on.
Yeah, I still would have got a correct answer, but that is not, that mathematically would not have been correct, because that would have been -4 pi. Put these together would have been -3 pi. Or no, -4 would have been -24, and then that would have been -23 pi over 18. But it still would have worked. All right, let's keep going. How about this? Two cosine squared. Let's use something other than x. Let's use theta. Plus cosine theta plus 1 equals 0. Now this should look different, does it?
A little bit.
Yeah, we have 2 cosine terms in here, don't we? We have a cosine squared term, and then we have a regular cosine term, and then we have another term that doesn't have any cosine in it. So if you squint your eyes, this looks a lot like what type of equation that we've done before. Quadratic, doesn't it? Doesn't that look a lot like a quadratic? Now, every semester it's different with students, like how easily they can see this or not. Some students need me to make a substitution here, some don't. So let me show you both ways. All right, so if you struggle with this at all, you might need this substitution. I have to first see that this looks like a quadratic. Quadratics look like ax squared plus bx plus c equals 0. That's a quadratic equation, right? So you have like the variable squared, the variable to the first power, and then no variable. It's kind of like what we have here. It's kind of like a variable squared, variable, and then no variable. So if we make a substitution, I could say let u be cosine theta. And then what I'm going to do is rewrite this equation. So if I rewrite the equation, I replace all my cosine thetas with u. What does this term right here become? 2u squared plus u plus 1 equals 0. Agreed? And now the question is, can you factor that or use quadratic formula? I believe it factors. So this should be 2u. We should have a u here, a 1 here, and then, wait a minute, did I copy this down right? Oh, this was a -1, I apologize. That was about to not be able to be factorable. Yeah, change that to a minus. My apologies. Change that to a minus, that's a minus, okay. And then we do, got that backwards. Minus here, plus here. So I'm trusting you could factor this. That okay? And now you would solve each of these. So if this one, if you set 2u minus 1 equal to 0, you get something. Here, u plus 1 equals 0, you get something else. This would give you a half, and this would give you -1. Is this clear, other than my negative sign mistake? You all right? Now, what was u? Cosine theta. So this equation right here is saying, the bottom left is saying cosine theta has to be a half. And the other equation is saying cosine theta has to be -1. Right? we finally have it reduced down to something that's doable on our unit circle. So where on the unit circle is the x-coordinate, because it's cosine, where's the x-coordinate? A half. Here and here. Is there any way to kill both those solutions out in one shot? No. You have two sets of general solutions here. X is what? X is what? Okay, so first one, pi over 3. That's going to start you out here, and then plus 2 pi n. That'll take you all the way back to it. How about the next one? 5 pi over 3 plus 2 pi n again. Jumps all the way back around. Does this make sense? Are y'all all right? Okay. You still have this to do, though. Where's cosine negative 1? Where's the x-coordinate negative 1? Right here. We're only going to have one answer there, like one general set of general solutions. Its x is pi plus 2 pi n. Why do you have to put the pi in front of the 2 pi plus 2 pi n? That's where you're starting at, right? You have to start at pi, and then you do your full revolutions. 3 sets of general solutions for that one. All right, I think you're ready for one on your own. And I want you to work together on this. I'll give you a slight hint, although this hint might be too much of a hint. Sine squared theta minus cosine squared theta equals 1 plus cosine theta. Do you want the hint or not? No, you know what? I'm not going to give you the hint. Okay, I will give you a slight hint. It's not the hint I was going to give you, though. The slight hint to this is this looks a lot like the last equation, except you've got sine squareds in there. Mixed, like if that wasn't there, this would be very much like the last problem. This would be kind of like a quadratic, wouldn't it? If that sine squared wasn't there. But sine squared is there. All right. Talk to each other. Try and figure it out. There is a way through this one. It's not super difficult, but it requires one little thing. Yes?
I don't want to say all that.
Okay, hold on. I'm going to mute my microphone.